All right, welcome back. I know, right? If your introvert starts by setting the tone of language, you can go ahead and follow that. But wait for them. Yes. You should invest in their pyramid first as a gesture of good faith.
All right, thanks.
Yeah, you should be set. That's definitely going to come up in all your interviews. All right, so continuing on. So this is our session of things that, like those interviews, gave you somewhat of an introduction to. Things that you don't really use a lot when you're coding, but are very relevant for a very specific subset of the interview process. So, because you've had some of this process before, but that was last week or this week we had Twitter come in? Last week? So what was your experience like getting in front of a whiteboard and going through some algorithm problems? Horrible? Good?
It's a pity.
I hear horrible, I hear pity, other good words. It's great. All right, that's a good one. So it's a mix, but hopefully that gave you a more realistic sense into what this process actually looks like when you're sitting and talking with someone. The things that are emphasized almost always are how effectively can you communicate your understanding of the concepts. Even if you're not getting the answer right, if you're doing a good job communicating that you understand what's happening, that buys you a lot of points with your interviewers. So the goal of preparing for those is making sure that you have conceptually strong understandings of the topics that they might be asking about. Now, in that you were asking primarily, I think it was FizzBuzz and what was the other problem? Matrix of the diagonal sum matrix. You've reviewed those? We can go over those again, but FizzBuzz, you should just drill until it's second nature, since that's a standard, do you know how to code coding question? That doesn't mean you don't know how to code if you don't know it, it just means you haven't studied that particular way of thinking about when should you be modding, where should your conditionals be, and whatever. But just make sure that you can do FizzBuzz off the back of your head. Yeah.
Using FizzBuzz as an example, how simple should we make our solutions?
How simple should you make your solutions?
Or should you just rig up the if-else statements and then just do it that way? Or should you try to do something fancy to
in general, the simpler your solution can be, the better. If you have an answer when you're this works, but it seems very simple, that might mean it's a good answer. With the one caveat of runtime complexity. So some of the problems that we've seen so far, the better solutions are actually not as simple, but they work faster. So an example is sorting, right? Bubble sort was a pretty easy to understand algorithm. Take stuff and keep swapping it. Merge sort was a lot more complicated. We're going to cut things in half. We're going to do it recursively. We're going to keep cutting it in half. When we get to the bottom, we're going to build another function that takes in two sorted lists and then combines those. We're going to call this function. That's a lot more complicated, but it's faster. So the answer should always be within whatever class you're trying to solve for. It should be the simplest possible. Now you're asking very specifically, should I have a ternary and try to make it fancy or an if else? In general, there's no hard and fast rule, but you should make as many variables as you need to understand the question, and you should have your conditionals be as explicit as they need to be to understand. With a couple caveats of try not to avoid the if thing is true. There's some quality of life stuff where you can just avoid this part here since it doesn't have any semantic meaning. But in general, simpler is better. Yeah.
We've been talking a lot about sorting in our DSA session.
Mm-hmm.
So in mock interviewing, I haven't seen any sorting questions.
Yep.
What percentage or how likely are you to get a sorting question?
So very rarely will someone just straight up ask you to build a sorting algorithm. Because I don't think it's very interesting, and if you've memorized it, you can just do it. What they might ask you is to do part of one or use part of the tactics of one of them to solve a different problem. So an example would be the merge sort part of the merging sorted algorithm, sorted arrays part of merge sort. That's a question that multiple people have gotten straight up as an interview question before. Write a function that, given two sorted arrays, returns a single sorted array. That question there is something that is totally fair game for people to ask. For something or maybe do a variation on something where, I've seen this one on lead code, for bubble sort, do bubble sort, except instead of only looking at two elements, look at collections of three and then order all of them before moving on. Right, so variations I think are more fair game for that. What you might see also as well is using some of those tactics to solve other problems. So what we're going to see, especially as we start to look at tree stuff today, is that some of the general recursive strategies that we've looked at with merge sort and quicksort are also applicable to some problems you might see with tree schema. So the answer is, it would be not a great interview question if they just said, do quicksort for me. But they'll definitely need you to know how fast sorting takes, and they might press you a little bit on why. Right, so like if you're doing like second smallest, and you start off, I'm going to sort the array, and then I'm going to give you the second thing in it. A fine solution. They might say, okay, how long does that take? And you need to be able to say, it's going to be n log n, where it's better than quadratic, but worse than linear. There's a lot of stuff, but it's honestly just a matter of practice. And it's okay if right now you're like thinking of this as like, hey, I can write some simple algorithms. There's a lot of this stuff that I'm not that like sure of right now. That's okay. These are more to give you an introduction to the general idea of what you're going to be going over. And then as you start getting into the like new year period, we're going to be revisiting a lot of the concepts we've seen to be doing more of a focused preparation on these types of problems. So with that, I cleaned a little bit up. I'm still working on it, but I put together just like a, and so you don't have to trawl through Canvas on Pursuit Core DSA. The links are all still there in the other place, but I just added links to all the labs we've seen so far. This is just pinned at the Join Pursuit repo. I will continue updating all of these, and there's also just a bunch of problems here as well for practice. LeetCode is another good source, but I'm going to continue updating this. But this should be a general source. If you're like, hey, I want to be reviewing linked lists, or I want to be reviewing queues or stacks. Like this is where the content, where you can find the content from it. Other questions on just like, hey, I interviewed with someone and I liked some parts of it and didn't like some other parts of it. Which side are you thinking about? Yeah, how other impressions from your interviews? Or any other questions that you had from it? Yeah.
If you're not feeling like the interviewer is really invested,
Mm-hmm.
you know, or emotionally involved, how do you go about like acknowledging that to them directly so that they can be a little more involved and present?
It's a good question. In the context of a mock interview, the best thing you can do is probably communicate that feedback to like a staff person later. In an actual interview, it is almost never going to be productive to comment behaviorally on anything your interviewer is doing if you're serious about the opportunity. You can say like, hey, I'd appreciate if you spent like, you know, like we're doing this. But if you say that, you're pretty much done from the interview. Like you can't. Like you can take it as like I don't want to work here and I want to communicate this to them. That's totally fine. But you should know if you're giving like behavioral comments to an interviewer, they're just going to flag you and say like, I don't want to work with someone who's correcting me in an interview. Like 99% of the time. Yeah. Some strategies you can use without directly addressing them to build investment and motivation is when you're approaching a problem, it often helps to speak in first person plural. So to say like, so what are we trying to solve? Like, okay, the first thing that we're going to do, and that can be a way to build investment, is it gets them to be thinking about it as more of a collaborative problem-solving experience, and that can help get in the mindset of like, we're doing this as something together. But you will find bad interviewers, guaranteed. Tech people do not get their jobs because they're good interviewers. They get them because they're good at solving these problems, maybe, or other things. That does not mean they're going to be a good interviewer. You'll have interviewers who think they have a right way about doing it that's different from what you think is right, and maybe their way's worse, but they're going to insist on it. You'll get interviewers who the only thing they care about is that you like know how to use a coalescing nil operator. That's it. Like you do everything else right. You didn't do that one thing, and then like they don't care about that. They're capricious. They're fickle. That's just kind of the world of like you have a bunch of people who are not trained in it necessarily, who are like going through the process. So if you're not invested, you can feel free to tell them. You can use some techniques to try to build their investment, but it's just going to happen at some point. Yeah. Okay, so with all that, we've looked at all these things one way or another so far, and what we're going to look at today is a little bit of an introduction into one of the last topics that's important in the DSA universe, which is that of trees. So, what's a tree? So let's say that you have a diagram that looks something like this, and you want to come up with a way of modeling it. So this is a very serious and scientific way of determining what product you should use to solve a problem. The flow chart, you say, does it move? If it doesn't, should it move? Then use WD-40. And if it doesn't, then you're fine. So this is a new kind of problem or a new type of diagram that we might want to model. We could model things with stacks like a bunch of plates, or you could model things like a stack inside of like a back button functionality in a browser could be a model for a stack. A queue can model things like a line, which is why it's called a queue. A linked list can be used to model things like an array can, when you have a list of sequential things that you're concerned about, like a baseball lineup or something like that. This is going to require something new in order to model this well. So this is, instead of being a straightforward list, we have a different kind of relationship between objects here. Every object doesn't just point to one thing, but points to two things. Right? There's a couple different options that we have after each one. Other types of problems that are involving this are like flipping a coin. Right? You flip a coin and then maybe it comes up heads, maybe it comes up tails. And then you flip it again. Maybe it comes up heads, maybe it comes up tails. If it was in this case, maybe it comes up heads, maybe it comes up tails. So if you're thinking about how to model or conceptualize all the things that can happen when you flip coins a lot, you would also want to use some type of branching structure like this. We have not yet seen a way that we can be modeling this very effectively using an array or a linked list. Hash maps can kind of track groupings, but they don't really have the way to get this order and sequence of things connected to things in this very specific way. So what we'll need for that is a new type of structure, kind of like a linked list, but instead of just having a next, you can have a left next and a right next. And from that simple-ish way of just changing it to say, oh, it's a linked list, but add one more thing, there's a lot of interesting complexity that follows from it. So that's a general motivation for what a tree is, what it does. Places in where like trees are used to model information, the probably biggest one is more in the web world, but if you ever go and look at like the HTML of a website, the best way of thinking about that is to be modeled like a tree, where you have your big root node at the top, and then all the other stuff follows from there. If you look at the XML inside of a storyboard file, it's modeled similarly, where you have a parent that has multiple children, and each of those children can have multiple children, and each of those children can have multiple children, and so on and so forth. The structure for modeling something like that is best modeled using a tree. Like when you go and click on the View Debugger Hierarchy button, this is actually an Xcode project. But, you know, when you click the button at the bottom and can see all the different views exploded and expanded out, and to the left it shows the relationship from everything. And your view controller might have one view inside it, and that view might have 3 views inside of it. And each of those views might have 2 different views inside of it, and so on and so forth. So this structure, how does Xcode model that? Like, how does it keep track of all that information? It uses a tree to keep track of it. So with that, let's get into a little bit to how we can build our own trees inside of Swift. So conceptually, a tree is pretty simple. Let me open from here. Okay, so conceptually, a tree is just going to be like our linked list, except instead of just having a next, it has a left side and a right side. So we're going to make it have some sort of value.
It is always like one or the other,
You're saying a left or a right?
true or false.
Oh, it could be both a left and a right.
But it couldn't be like a left, middle, and a right.
It could. So this is a special type of tree that, if it's just, what would you call that if it can just be on or off, or like only 2 options? A bool, and if it's only 2 options, binary, right? So you're totally right. You can build a lot of different trees. One of the trees you could build would be something, like I gave an example with like heads and tails, right? Where there are only 2 options. But what if you're rolling a die? Maybe then say, okay, I roll a 3, and from that I can get a 1, 2, a 3, a 4, a 5, or 6. This is also a tree. Generally, when people talk about trees, they're talking about trees where there's only 2 possible children, and that special kind of tree is called a binary tree.
Yeah. So a binary tree specifically, that's a very good specification, has some sort of value. We'll just have being int for now. We can go and refactor that later. It has a left side, which is of type optional tree node, and a right side, which is also of type optional tree node. Then to build one of these, we just need to pass in the value and then assign it. Because these are variables and they're assigned here to optionals, they have a default value of nil. You can write that in yourself if you want to make it explicit. So this is the basic structure, just like a linked list is just like the next. A binary tree node has a left and a right instead of just a next. So you can contrast this with the implementation of a linked list node. So this is something we've seen before. A linked list node would have a value, and it would just have a next, which would be of type linked list node here. So they're very similar in terms of their implementation. The difference is just how much stuff they point to. And just like we have a linked list node can point to 1 and 0 things, our binary tree node can point to 0, 1, or 2 things. We can also make something that pointed to 0, 1, 2, or 3 things, or make something that pointed to any number of things, and it can get a lot more complicated from there. For now, we're going to stick with this as our tree node here, working with primarily binary trees. So that should be in the back of your head as we're thinking about modeling it. In terms of some terminology, people really like making lots of special words for different trees that look in different ways. So I'm just going to review a couple of these here for some vocabulary. This is an example of a tree structure here. The very, very top of a tree is called the root. And this picture is generally how you'll see trees organized when you're looking at it graphically. The tree node, so 8 here, this top circle would be a tree node class. 8 would be its value. And then that 4 at its left would be its left, and 12 at its right would be its right. 12 is said to be the parent of 10 and 14. So people use a lot of just like family trees are a way of storing information. People use a lot of that same verbiage and terminology to talk about trees in computer science. So you talk about parent nodes and child nodes specifically. So every parent in a binary tree can have 0, 1, or 2 children. And every child can have only one parent. So the analogy kind of falls apart a little bit, but in our binary trees, the 10 here can only have one parent node. If the 10 also is connected to the 8, it wouldn't be a binary tree anymore. It would be something else. It would be what we would call a graph. So you have your root, you've got parents, you've got children. And a really interesting part about trees is you can just look at a snapshot of it, just look at a section of it, and it's still a tree. But it's part of the whole bigger tree. So if you look at this little 4, 2, 6 cluster here, it's part of this tree, but by itself, if you just got rid of this line, it would be a tree all on its own. So we call this little cluster a subtree, because it's part of the bigger tree. And a lot of problems that you solve with using trees require thinking about breaking down a tree into all of its different subtrees. So that's a little bit just in terms of terminology from this year. Couple more things. At the bottom, any node that has no children is called a leaf. So it's going back to the tree away from the family, instead of like a, I don't know, parent with no children or something. You call an edge is something that connects 2 nodes. The level represents what kind of row of the tree it's on. And the height of a binary tree is how many nodes you have to go, or how many edges you have to go down to get to the bottom. So just some vocabulary, and I guess you call these 2 things siblings. So if you've ever seen a family tree before, you can probably just pick and choose from those words, and they'll largely make sense. I don't think people say that like 12 is the uncle of 6 or something, but aside from that, everything else I think carries through. So and the level is which row it's on. The root is at level 0. So an interesting thing with the height of binary trees is you can see that as you start going down levels, you start to get pretty crowded at the bottom with more and more children, right? You start off with 1 parent, then you have 2 below, then you have 4 below, then you'll have 8 below, then 16 below, and hopefully that pattern is something that's familiar when we're working with binary numbers, because it's powers of 2. Come back to that. So, there's a lot of different types of trees that we can make. We have been talking primarily about binary trees. So binary trees, an example of one here, every node has either 0 children, like this one here, 2 children, like this here, or 1 child, like this here. And not binary tree would be something like this, where we could have multiple different children here. So this would be like, I don't know, do they make 3-sided dice? Is that a thing you could have? Like maybe like a triangle with like tapered edges or something? Was that? If it's a pyramid, you could have like a cylindrical thing, you know, like a pencil, but like only 3 sides. Okay. Anyhow, let's say you had one of those. This could model like the different possibilities you had. What? I guess that'd be a triangular prism. Yeah, triangular prism. A triangular prism that's like really long, like this here, so you couldn't you don't care about the sides of it. Yeah, a triangular prism ignoring the sides. There we go. Okay, anyhow, so this is not a binary tree. This would be, I suppose, a ternary tree, you could call it, or just an n-ary tree. Some more vocab people like putting in. This made it look a little odd. You're like, hey, why does this one only have 1 child? A lot of times people like to fill up the trees first, so there's some specific words that people use to talk about how to fill up a tree before going on and adding things in other places. A full binary tree is something where every node has 0 or 2 children. So it means that we're not allowed to have stragglers like we do in this example, where the 5 has 1 child and the 9 has 1 child. A full binary tree means we either have 0 kids or 2 kids. Children, I suppose I should say. A complete binary tree is a binary tree where every level, except for the last one, is completely full, using this definition, and everything at the last level is as filled as possible towards the left. You're allowed to have 1 node with 1 child, everything else after is 0 or 2. So this is an example of a complete binary tree. It's as full as it can be, and you have 1 straggler that's all the way as far to the left as it can be. So the idea is that a lot of times when you're trying to figure out how can you make your information more compact, you want to avoid grabbing this subtree here and moving it here, because then your tree is longer than it needs to be. It's taller than it needs to be. It has a bigger height.
Is it a complete tree only have 1 single or only 1 level that has singles on it?
It's allowed to only have the last level is allowed to have 1 single. Yeah. And then this would not be a complete binary tree here because you have what is it? Because you're not full, and because you have a depth that's too far down to the side here. It's convention. I mean, you can model it differently if you wanted to.
How is that not full then?
So to be a full tree, you have to have every level except for the last completely filled here. You can see that this level here isn't completely filled. So level 0 is filled, level 1 is filled, level 2 is not filled. So in order for this tree to be a complete binary tree, you'd have to take these 2 nodes here and give them as children here. Then it would be complete. People also talk about balanced binary trees, where the left and right subtrees' height differ just by 1. The idea is a balanced binary tree is one that doesn't go super deep on one side and not very deep on the other one. This is what I was talking a little about earlier of how the tree grows in terms of its height. A balanced binary tree is one where the height of it is the log of the number of elements. So as you draw out the structure of the different options that you have for your tree, you end up with, we have our initial flip here, we then have 2 children here, each of those has 2 children, each of these has 2 children, and so on and so forth. We have 1 thing here, 2 things here, 4, 8, and then the next row would have 16, and so on and so forth. We're able to capture 8 things within 3 levels. So this is our row number here.
we're able to capture 16 things in 4 levels. We're able to capture 32 things in 5 levels. If this is true about the tree that you've drawn, then you have a balanced binary tree. The way it wouldn't be true is if you go off the rails, instead of trying to fill up one of the levels, you just start taking a wild chase down like one of the nodes for some reason. This tree is not going to be a balanced tree because this subtree is way too big compared to this one here. Like the left tree like has a height of like 7 or 8 here, and the right subtree only has a height of 3. So you want to make sure when you're building these that there can be balance so you can be getting that nice logarithmic structure. Yeah. It is the same image. You can have a complete tree. I think complete trees have to be balanced. Yeah, I think complete trees, you could have a balanced tree that might not be complete. For example, like if you moved this node here over to here, it would still be balanced, but it wouldn't be complete anymore. So the idea is that every balanced tree is going to be yeah, that way. Yeah. So, because you could change around this balanced binary tree and not change the heights. That's the thing that they care about is heights. Complete trees care about heights and they care about other stuff. Yeah. And then the last fun one is a degenerate tree. A degenerate tree is one where every parent only has one child. It's just a linked list. So this one's good fun. You've worked with plenty of these, and a lot of times when we talk about different algorithms for trees, we can talk about their behavior degenerating to like bad run times if your trees start to look like linked lists. It's still like if you use a tree, and it still could have another child. Yeah, it just has nils everywhere, right? Like you could say like, oh, like a linked list that just has one element that doesn't point to anything isn't really a linked list. They're like, but it could have an X if we built it better or gave it one. So it's a lot about how you're organizing the data and what options it has available to it. Yeah, if you just don't give an option to have a left and you only give a right, then you're just building a linked list. People also talk, man, there's a lot of this, about binary search trees. We're not going to actually build one of these, but it's an important word to know about. A binary search tree is a special kind of binary tree that's built very cleverly, where every node in the left child subtree is smaller than it, and every node in the right child subtree is bigger than it. So you can see if you organize your data like this here, where going to the left is smaller and going to the right is bigger, you can do a pretty good job finding information pretty quickly. You can also use min and max heaps to build information similarly, where the top level is the smallest, and then as you go down levels, you get bigger. Or a max heap where you start with a big value, and as you go down, you get smaller. People do these here because you can find information much faster if you're organizing it with this structure. Okay, so tons of vocab there. This is mainly here as like a resource for something to look at. I've heard, unfortunately, like one person actually getting questions about like complete trees versus full trees. I wouldn't spend that much time worrying about it. It doesn't come up that often if people are asking about it, but it might come up, and so it's here as a resource. The main thing to be concerned about with binary trees is traversing them. So unlike with like an array, traversing an array is pretty straightforward. You just have a folder. Traversing a stack, that's a little bit, but largely was straightforward. We just need to pop off the stack until we're empty. Traversing a queue was kind of the same, right? Just keep dequeuing things until you're out of stuff. Traversing a dictionary is also like, go to the underlying array and then just tell me all the stuff that's inside of it. The tricky thing about trees is that traversal is a little bit more of an interesting problem. If there is one thing to know about trees, it is how can I read all of the values in a tree given its weird looking structure? This is the bulk of what I want to go over because it's the most likely one to come up in the context of an interview, and a lot of other problems that involve trees require you to understand different ways about iterating through them. So, given that we have a tree that looks something like this, how can we actually read all of the values? Yeah.
Start from the root
Mhm.
and keep going down the left child until you reach the end,
Mhm.
and then go back to the second level, and then go to the right child,
Mhm.
from there, to see the left child,
Mhm.
and then you go through that process.
Yeah, that makes sense. So like, you're saying like, just keep hugging left, and then when you find something, and then when you get to nil, like, back up, and then try to go right, and then when you find nil again, back up. How can we represent that with code? So it's a little bit of the like, when we have a for loop that does that, like, do we just like start chaining together like dot left, and then until we end up at the end? Yeah, we're gonna have to use a recursive strategy. We know that we want a recursive strategy for this year because we are explaining a problem that can be broken up into a bunch of different parts. How can we print out all the nodes in a tree? Well, just print out all the nodes in the left side and the right side. Well, how do I print out all the nodes in the left side? Well, just print out all the nodes in its left side and its right side. Well, how do I do that? Well, print out all the nodes in its left side and its right side. Okay, like I can do that because there's only one and it doesn't have any children. And then you can go through that process. So that's the general idea of what traversal looks like for a tree. What we're going to do, we'll draw this out here, is in order, our problem is we're given this as an input, and we want to print out all the nodes. To print out all the nodes in this tree, we can print out a 1, and then print all of the nodes in this tree, and all of the nodes in this tree. To print all of the nodes in this tree, we can print out a 2, then print all of the nodes in this tree, and all of the nodes in this tree. To print all of the nodes in this tree, we can print out a 4, and all of the nodes in its tree, and its tree here. To print all the nodes in this tree, we don't need to do anything, because there are no nodes in a tree that's nil. Same thing here. And so then we've printed out all of the nodes inside this 4 tree. Then because we've done that, we can do the same thing for 5. Then we've printed all the nodes out in its subtree. Because we've done that, we printed out all the nodes in this subtree here. Then we back out again, go into the right side, and go through that same process. It takes a little bit of time to get used to, but let's go ahead and code up what this looks like, and then walk through really explicitly each step of the process. So what we want to do is traverse this tree here. So we're going to call a function here traverse. Our traverse is going to take in a tree node, and it's going to return nothing. All we want to do is print things. Again, we could make this genericized, we're just going to keep it in for now. So, all we want to do is print these things here. Now, what we want to do first is say, if you gave me nil, I actually don't need to do anything. If I say, here's your tree, it looks like this. It's fine, it's actually they're talking about DOM manipulation stuff. That's another tree right above here. If I give you this as a binary tree, and I ask you to print all the nodes, you don't need to do anything. You can just return. So we've got our base case for our recursion. You don't give me anything, and I will go ahead and not print anything. Equals root, else, return. So there's our base case. Now, as with recursion, let's start at the bottom for the simplest cases and then work our way back. If the input was only this right here, this 7, what we'd want to do is say, okay, let's go ahead and print that 7. Then we'll go ahead and try to call it on the left side and the right side, but we know those are going to both be nil in return. So let's imagine that 7 in your mind is the thing we're talking about here. To say, okay, the root isn't nil, it's that 7. So what we want to do instead is say, let's go ahead and print the value of that root. Then we'll go ahead and call traverse on the left side, which we know is nil right now, and the right side, which we also know is nil right now. So what this will do from the 7 is we'll print out the 7, and it will call it on the left side of nil, so we'll just return immediately. It will call it on this side, which is nil, and return immediately. And then we're done, so we'll just go ahead and return.
And believe it or not, that's actually all the code we need. Recursion is a very interesting thing to be working with.
The same thing that works for our nil and for our 7 will work with the entire tree, like tree of any number of nodes. And that's the power of a divide and conquer algorithm, is if you can think of it in terms of like building up from smaller pieces, then you're able to solve simpler problems that will do the same work as more complicated ones. So let's kind of step through what this is doing. First, let's go ahead and build this tree out in code. It's a little bit annoying. There are nicer ways to do it. We're just going to do it super old-fashionedly. Let's go ahead and make our, just going to call this 1. Not a great name, but we're going to make all of our nodes here. And then we're going to link them all together. Tree node val 3. How many do we have? 5? 4 is tree node val 4. 5 is tree node val 5. And let's add a 6. Oh, we have a 6 and a 7. But 6 equals tree node val 6. 7 is tree node val 7. Let's go ahead and make an 8 as well. While we're at it, I'll slack all this out so you don't feel compelled to copy this. Now we need to hook them all up. So we want to go ahead and say that 1's left is 2, 1's right is 3, 2 has a left of 4, 2 has a right of 5, 3 has a left of 6, 3 has a right of 7, and where do we want to put our 8? Our curveball piece. Put it down here. Give it a little curveball. Our 6 is going to have a child of 8. So we're no longer a complete tree anymore. That's okay. We're still balanced. So we'll go ahead and take 6. We'll have a left of 8. I will slack out all of this here, just so that you don't go in too deep. Okay. Create new code snippet. Snippet. Great. Okay. So this is the tree that we want to traverse. Let's go ahead and see what we're printing as we traverse it, and then try to figure out why it ended up doing that. So we're going to go ahead and call traverse. And we're passing in 1, because that's the top of our tree here. Then we'll go ahead and run it. Okay. Where's our error at? Values before being initialized? No. It's our linked list implementation. So that shouldn't matter at all. Yeah. Man. Probably can hear my computer from the last row. This is very overactive right now. Okay, great. So again, we ended up printing 1, 2, 4, 5, 3, 6, 8, 7. That wasn't in order, but we printed something, right? So let's sort of walk through and figure out, why is this what we're printing here? How did we actually end up with this as the sequence that we're talking about?
I got 1, 3, 7, 6, 8, 7.
You got 1, 3, 7. You have 2 7s? You got a mistake somewhere if you got 2 7s. You have 3 7s. That's too many 7s. That's too lucky. Okay. So let's go ahead and walk through what this is doing and figure out why it's printing this here. The first thing that we do in our function is we say, if the thing that you've given us is nil, go ahead and return. Well, we're given 1 as the root. Well, that's not nil, so we're going to go ahead and do the first thing, which is print it. So far, so good. Then we're going to call
recursively on the left side and the right side. So we're going to say, okay, now call traverse here. And before we can call traverse here, code runs top to bottom. We need to actually finish traversing the left side. So we haven't actually traversed anything on the right side yet, because we're still traversing the left side. So great, so let's start executing traverse passing in this 2 here. Well, the first thing that's going to happen is we're going to print this 2. Then we're going to call traverse on the left side. Okay, this is still not nil. So what we're going to do is we're going to go ahead and print this 4. And then we're going to print colors. Yeah, one of the blue one was. Then we're going to call traverse on the left side here, which is this nil. So now we're traversing nil here. Before we print, we first check to see if we're nil. Well, this one is nil, so now we're just not going to do anything. From this call here, this 4 has passed in its left side. It's finished line 23, so now it can go on to line 24. Well, that's also nil, so we return. Now, this call here, we finished that execution that returns. We passed in 4, we printed 4, we looked left and we looked right, and we completed the code there. It's done. Our 2 is kind of next in line in our call stack. It's printed 2, it's finished going left, so now it's time for it to go right. So now our 2 can go ahead and go right, print out this, print going right, prints out this 5, and then it will try to read left, find nil, read right, find nil, then it's done. Our 2 has then printed itself, gone left, and gone right, so it's done. Our 1 has printed itself and gone left, so now it's time for it to go right. The first thing we do is we print this 3, then we go left. The first thing we do is we print this 6. The first thing that we do is we print this 6. Then we go left. The first thing that we do is we print this 8. Then we go left and we find nil. Then we go right and we find nil. We back out to the 6. We went left, so we go right. We find nil. We go back to our 3. We went left already and finished it. Now we go right. We print this 7. We go left, we find nil. We go right, we find nil. We're done, and then this is our sequence that we printed. Not a lot of code, a lot of complexity. It's kind of the nature of recursion in general. So we're able to traverse this whole tree here by using the same structure for all of it. And it's always helpful to think of starting at the bottom level. What happens if I pass in nil? And what happens if I pass in a node that doesn't have any children? And make sure it works for that. And then it'll probably just work for the whole tree. Yeah. That's a good question. So we have to, what's the time complexity of this here? How are you defining n is one of the questions. So if you're defining it by the number of nodes, we visit every node once. And so because we visit every node once, and we don't repeat visits, you could say it's O of n, where n is the number of nodes for traversing here. If you wanted to define n as the height of the tree, then it's like 2 to the n, right? Because if you have a tree where you're talking about n is the height, and you could have a height of like 3 or 4, you'd have to make a lot more visits relative to that. So typically you'd say relative to the number. Yeah. So the question is, what does it mean to be able to define what n is? In big O notation, we've been able to use the assumption generally that n is the number of elements in the array that we have. It can get a little more complicated because sometimes you can define n to be, so n has to relate to the things that you're talking about, right? The thing that's scaling. That could be that's the number of elements. But as you increase the number of elements, the height of the tree also grows. So if you wanted to, you could define n to be the height of the binary tree, rather than how many things are inside of it. And that would be equally valid. It probably makes more sense in this context to talk about it as the number of things that are inside of it. But you can choose to define n
through other ways if you wanted to. So like when you're talking about a matrix, for example, you could talk about n as the height of the matrix, but it probably makes more sense to talk about the total number of elements. Okay, so we've gone through one way of being able to write out all of the things that we see when we traverse this. Now, we chose to put our print statement at the top. We didn't have to do that. As long as our print statement is somewhere, we're going to end up printing it. If your print statement is at the top, that's called a pre-ordered traversal. We could instead put our print statement in the middle. This is what's called an in-order traversal. Putting it in the middle here, we'll end up with a much different order of how we are ending up printing things. The first thing we print now is 4. Well, how does that happen? In-order traversal means after you're done going to the left, then print yourself. So we start with 1, we go left, we're done going left, we print 4, we go right, we're done. We go back to the 2, we're done, so 2 is the next value, we're done going left, so we print 2, then we go right. We go left, we're done going left, so we print 5. We go back, we're done going left, so we print 1. Now we go to the right, then we go to the left, we go to the left. We're done going to the left, so we print 8. We're done going left, so we print 6. We're done going left, we print 3. We go to the right, we go to the left, we come back. We're done going to the left, we print 7, and then we back out all the way back to the top. So that's a in-order traversal. And then naturally, the last way that we could do it would be a post-order traversal, where instead of printing in the middle, you print at the end. Print root.val post order. And what post order will do, pre-order said, before you do anything, print yourself. In order said, when you're done going to the left, then you can print yourself. And post order is, once you're done going to the left and to the right, you can print yourself. So we end up here with an ordering that will go through. Okay, so we end up here with our post-order traversal, saying we're going to go left, we go left, we go left, we come back, we go right, we come back, we're done, we print 4. We go left, last time we printed 2, but we're not done yet because we're doing post-order. So we go right, done, we print 5, we come back to 2, we're done, we print 2, we come back to 1, we're not done yet, so we don't print 1. We go to the right, we go left, left, we're done, we print 8, back to the 6, 3, we're not done yet, we have to go right, 7, done both sides, print the 7, print the 3, and then the last thing that we do is we print out the 1 where we started. Now with all of these structures here, you'll notice that we never ended up printing the 2 and the 3 next to each other. The structure that we have is we said go left, and go left, and keep going left. And if we had a bunch more nodes here, we would end up going all the way down to the bottom before we ever thought about going to the side here. For that reason, this whole traversal strategy is called a depth-first search. So this traversal here is a depth-first search. What that means is the thing that we want to do first is go as deep as we can before trying to look at anything around us. Examples of when this is a good strategy might be like, let's say you're trying to get out of a maze or something, right? You could think of a maze kind of like a graph or a tree. You might want to just like take one of the routes and try going all the way through on it, and then you see if you get a dead end, and you take a step back and you try all the other routes. So that might be a good one for just trying to get to the end. Now, that's a good strategy if what you're looking for is at the bottom, right? You want to traverse because at the bottom of one of these is a node that's like the exit node, and you want to get there. That's not the only strategy we might want to employ. It's possible that we might want to know things that are close up to the top, but we don't know where it is. So an example might be like, let's say we have that min heap set up, and we're looking for a number, and we know it's a small number, so it's going to be near the top. We don't want to have to go down the whole way first. If we know that it's a small number, we might want to stay up higher. Another strategy we can use is called a breadth first search, where instead of going as deep as we can and then backing out slowly, we'd say, let's go one level at a time and look at everything here, and let's look at everything here, and let's look at everything here, and let's look at everything here. Let's take a quick look at what this approach would look like as our other traversal strategy. We will need an additional data structure for this. This is going to be our implementation from before of a linked list. I'm just going to take Swift Algorithms Club because I'm being lazy. Swift Algorithm Club linked list. It's a great way to find data structures if you want them. You can use implementations we've built. Swift Algorithm Club is also an excellent resource for being able to build these kinds of structures. So, where is theirs? Can I actually just have their whole implementation? I gotta have it somewhere. There it is. Okay. So we're just gonna grab their linked list, and we don't care at all about their implementation right now. We're just gonna copy and paste this, and then use it. Again, we have literally no idea what their linked list is doing, except we trust that other people have built a linked list. We're using this in the same way that we use arrays all the time. Someone had to build an array. People at Swift Standard Library did, or a dictionary, right? We went through a dictionary implementation. You can do that, but we're just going to use someone else's. So how are we going to do our next traversal, which in this case here is a breadth. It's probably how I spell that. Breadth first traverse. We're going to have the same input where we're going to be traversing a tree node here. This strategy is not necessarily going to be a recursive one. It could be. Anything that's iterative could be recursive. But for this here, the reason why we took in our linked list structure is because, actually, we wanted a queue. Put it in the linked list. Nah. I'll grab a queue. Swift Algorithm Club queue. Thinking of how we wanted to be implementing it. Sorry about that. Queue simple. Perfect. All right, we're grabbing a queue. Get rid of your linked list. We don't want that. We want to, the queue is fine. Their queue is, we're taking queue simple. It's not a very efficient queue, but it should be fine for our purposes. Let's just actually see if they have a slightly better one to be stealing from. Queue optimized. Yeah, that's a good point. All right, let's assume this gives us good runtime performance. There it is. Enqueuing and dequeuing are not constant time. So let's go ahead and take their queue. So we've got a queue. Why do we want a queue? Because what we're going to be writing here is a new algorithm that's going to use the structure of a queue to keep track of how we're going to be putting things in. So here's what we're going to do. We're going to start off with our root here, just one. We're going to have a line, our queue. This is the front of the line. This is the back of the line. We're going to put one at the front of the line. When it's your turn, you exit the line, we print you, then we look at your children, and we put those in the line. So we'll take this one out, we'll print the one, then we'll take its children, 2 and 3, and put them in line. Then we'll go to this 2, and we'll do the same thing. We'll take the 2 out, we'll print it, and then we'll put its children, 4 and 5 in line. We'll do the same thing for this 3. We'll take it out, we'll print it, and then we'll put its children, 6 and 7 in line. And then we'll do the same thing with 6, we'll put this 8 in line. The line will keep track and make sure that we're processing things in their correct order. Because we'll put 2 and 3 in line first, and then even though 2 says, hang on, I've got more stuff that's interesting, we say, okay, put it at the back of the line. We'll get there when it's your turn. But we're going to have to process everything that one put in before we can get to the stuff that you put in. So what does this look like?
We want to first make sure that our root, should be lowercase, isn't nil. So guard the root, else return. Because again, you give us nothing, we give you nothing. Then we'll go ahead and make our queue. What's this called? Queue? I can give you tree nodes, presumably. Tree node. Let's see if this works. It's syntactically valid. Great. All right, so now we've got a queue, we've got our root. We'll go ahead and start off by putting our 1 in line. So we'll take our queue and we'll insert enqueue. We'll go ahead and enqueue our root. Note that we're not putting in just the value because we need to know what its children are. Then, while the queue isn't empty, so note also that I didn't even look at their implementation, but I knew it had an isEmpty because that's what a queue means. We want to go ahead and dequeue. We can force unwrap that, whatever happens to be the front of the line. So current node is going to be what happens when we dequeue. So we have the current node. Then we want to go ahead and print its value. Current node dot value. Then we want to put its children in line. So I think we said first you put your left child, then your right child. Could do it either way. So we'll go ahead and take the queue, and we'll unqueue the current node dot left, and we'll do the same thing for the right. We will get a compiler error here because our queue has non-optional tree nodes in it. So we could choose to, and we can't force unwrap it here because we want it to be nil at some point, otherwise our tree would never end. We could choose to either make it so that our queue can have nil things in it, or what we could do is we can just make it so that if we're only going to add a left or a right child if you actually have those children to add. So we'll do it that way. Equals current node dot left. Then we'll go ahead and unqueue the left child. And do the same thing for the right child. Current node dot right. Queue dot enqueue right child. Yep. I think I just searched Swift Algorithm Club, but I will give you an easier way of that. Create new. Okay, so now, while our queue, we're running through that algorithm that we just talked about here. While our queue still has things inside of it, we're going to go ahead and take it out of the line. We're going to return whatever its value is. And if it has children, we'll put those in the line. Note that we didn't do anything recursively for this one, because we don't really solve this differently. It's not really like we're breaking this down into smaller problems. We have a larger strategy that's taking it a little more holistically and saying, we're just going to do this for everything. We're going to keep adding children into this one list until this list is completed. So let's go ahead and run it here and see what we get when we put it inside our linked list here that we have. So we have our breadth first traverse passing in 1. And let's go back to our pre-order, because why not? So we're first going to print our in order, pre-order rather, pre-order, reverse, pre-order, breadth, depth, first search. There we go. And then we'll print our breadth first search. We'll see if we made their queue happy. Okay, so we can see that our pre-order gives us the same thing it did before. We just went back to that implementation. Gives us our 1, 2, 4, 5, 8, or, yeah, sorry. Yeah, pre-order. 1, 2, 4, 5, 3, 6, 8, 7 ordering. But our breadth first search gives us each row. Gives us 1, 2, 3, 4, 5, 6, 7, 8. The reason for that is because we're taking every row and making sure that first we're going to print all the children of 1. Then we're going to print all the children of 2 and all the children of 3. Then we're going to print all the children of this row. And by using a queue to make sure that everyone is waiting their turn in line, we don't have anyone jumping the gun like they did in the depth first search and being printed before people from other subtrees were even entered into the equation. So that's a bulk of what people might be asking around tree traversal. The two main things, kind of in summary, are, I'll slack out all this here. I think I have some notes at the bottom, but you can have those as well. So main things to remember with trees are some of the vocab from the trees we talked about before. In terms of traversal, there are two main strategies. There's depth first traversal, which says start at the root and go all the way down one path as possible before backing up. And there's breadth first traversal, which says I want everything from the whole level printed before we go to the next level. Within the depth first search of saying, let's go in super, super deep all the way down one of the rows of the tree before coming back up. We can choose to print values either before we've gone left or right, after we've gone left but before we've gone right, or after we've gone left and right and just go. None of those are better, they're just different strategies for how to be like conceptualizing the order in which you're looking at it. Yeah, so that's in terms of traversal. There's some clever things. The next steps to look at if you want to are to look more into binary tree traversals. So binary trees, we talked a little about, that's where the left side is smaller than the right side. You can do, that's fancier. They're pretty efficient for being able to find things because just like binary search works, everything on the left is smaller than everything on the right. So you can use that same chopping in half tactic, but it's like your whole data structure is built like that from the ground up. So binary search trees are really good at finding things because you can just do a binary search to find anything because your whole list of things is already in sorted order such that the left side is smaller than the right side and that the right side is bigger than yourself. Yeah. Great. That's trees. A lot of stuff on trees. Not expected, again, trees is kind of the first in the like enrichment-ish things. It's not really necessarily part of like a standard algorithm interview, but you definitely will have interviewers that will like expect you to know things about them. Yeah, so an example of a DSA question that would involve trees. A lot of the ways that DSA questions work that involve trees don't say you have a tree, but they are a problem that's best solved by using one. One example is, let's say, two-step, or one or two-step. I don't think I'm going to go through the whole solution here, but let's say that you are on top of a staircase, and you can choose when you're going down the stairs to either go down one step, or you can choose to skip. Yeah, you might have seen this before. You can choose to skip it and instead go down 2. The best way to be visualizing this is starting at the top and saying, I've gone down 0 steps so far. I can either end up having gone down 1 or having gone down 2 steps. And for each of those, I can either take the path to go down 1 or go down 2. And then the question might be, how many unique ways are there to the bottom, or something like that. So that's an example of a problem that wouldn't necessarily be you get a tree, but one that you might use a tree in order to solve. Another big one is like change making, another typical tree question. You're given like $1.34 or something. How many unique ways are there to make change? I remember we sat with that one a little bit before. We got to a solution for that, I think. Yeah, it's a fun one. And that was in the recursion log, right?
Because they're ultimately recursion problems, right? It's just a recursive problem that thinking about like a tree makes maybe a little bit more clearly in terms of it. So it's not, so you're building a tree in how you're thinking about it, but you're never actually saying like, let my tree node equals whatever. It's just that the structure that you end up making happens to be a tree structure.
For some specific tree questions, if you go to the link for the lab here, there's a list of, now these are primarily going to be tree questions, like explicitly about trees. One that isn't, this is just kind of a fun one. Technically it's a graph question, but this one is deceptively challenging. It says you start at the top of a 2x2 grid and you can only go to the right or go down. How many routes are there from the top left to the bottom right in a 20x20 grid? So this is technically a graph traversal question, but is modeled similarly. So these kind of questions that like are talking about possibility space often end up being tree questions. Hmm?
Well, when you say it's a tree question, if we were whiteboarding this,
Mhm.
we just draw a binary tree and answer that way, or we
Well, you have to write code. So the question is like, if you get this question, can you just draw the tree and explain it? That should be your first step. But if they're asking you this, you probably need to be writing code to do it at some point. But way better than if you can explain how you approach the solution, they can help you through that. What's much harder to help someone through is if you don't do a good job articulating how you want to solve it. So there's some other questions here I put in the link for the lab that's going over some binary tree questions to get a little more fluency around it. The first one, I'll just make a note, says, the code has been very slow. The first one makes a note that says like, hey, here's a tree traversal. The recursive solution is trivial. Could you do it iteratively? The recursive solution is not trivial. It is a little bit like challenging to think of. It is what we just wrote. It is only those 3 lines. But, you know, good to think about. Other fun ones that you see on these kind of problems, like this is a big one here, this number 3 for DSA type questions. Change making is one example of it. This one says you're given a binary tree and you need to figure out how many paths sum to a specific value. It's kind of like the change making question. So it's saying that you start at the top of the tree, you start going down paths, and you need to know when you've gone down a path and ended up with the right value. So these are all problems that you will see in this, in the wide, big universe of tree questions. But if you can look at the first 2 and feel pretty good about like maximum depth of a binary tree, which we didn't talk about yet, then that's kind of like if someone's asking you a tree question, it's probably not going to be more complicated than like number 2. They probably won't ask you a tree question, but they might. It's definitely more on the like, if someone's asking you a tree question, it's because they care about data structures and your knowledge of them. And so they have to have more of an opinion about that. Maybe they're a larger bank, they have like more of a standardized like way to be doing interviews, and they like value that kind of experience. But it's all just a matter of practice. Yeah.
So we solved,
Mhm. Yep.
we didn't use,
Yeah.
so in this case, we just
Yeah, exactly. So you're still building a tree even if you never make a tree object. You can still have a question that you're solving by using the structure of the tree. If you end up calling recursively on like, thing, like take out recursive Fibonacci, for example. So something that you've done before, like we've done before in our recursion like place. Fibonacci says f of n is going to be equal to f of 2 numbers before it, so Fibonacci. So you solve this here by finding the 2 out before, right? So when we drew out the solution to it, we didn't call it a tree, but we said, oh, well, you start, we want to find, the 7th Fibonacci number or whatever. They say that f of 7 is going to be equal to, wait a minute, 4th Fibonacci number. F of 4 is going to be equal to f of 3 plus f of 2. And f of 2 is going to be equal to f of 1 plus f of 0. And f of 3 here is going to be equal to f of 2 plus f of 1. And f of 2 is going to be equal to f of 1 plus f of 0. So remember how we talked about the structure before? Now, this looks pretty clearly like a binary tree, right? We never called it a binary tree, because we didn't need to make a tree node to solve the problem. But because our recursive call said, for everything that comes in, I'm going to make 2 calls, we ended up building a binary tree. Now, the runtime of this exploded for various reasons, but we've used these as a part of thinking about solutions before, without ever having made a tree node. We ended up building this whole picture in our call stack just because of the way that we built our recursive function. A lot of recursive functions end up building binary trees, or other trees with different structures and how they're being implemented. Like I said, we'll have some more practice with trees. It's something that can come up. It's like you should have this as a resource. The vocabulary should make sure that you're familiar with. And if there's anything to practice on trees, it's making sure that you understand traversals. And then the next level would be trying to think about solving some more of those questions like change making, two-step, that require you to be using tree structures and how you approach problems. Okay, I will make video stuff from this available. I'm working on all of those. YouTube just takes forever to upload. And yeah, that's some DSA here. Yeah. I've been struggling with YouTube for a little bit, but I'm going to be. I'll send a link and put it up on the same repo once I have like a place for them to be. Yeah, they should be up by the end of the week. Yeah. Yeah. So this should be the last new topic before like assessment stuff. So we shouldn't be going over much new DSA stuff. The only topic we haven't talked about at all yet has been graphs. We'll get there. That probably won't be part of anything that we'll talk about until the new year, though. Graphs have their own complexity, and it's less likely that you'll get a graph question than a tree question. Yeah. Yes? Yeah, for sure. Yeah, so a lot of what we're going to be doing in the new year especially, so the question is like to be solving DSA questions without having like we know it's about this topic and like here's like code for how to be doing it. Like when is that going to happen? Primarily in the new year, we're going to be going over like how to be solving these questions from scratch and a lot of practice with whiteboarding, which is really what that is. So we'll be building out better pools there. Yeah. It'll be a combination. Yeah. We're still figuring out what the structure looks like, but I will say with any of it, it's going to be okay if there's still stuff that you're working on. That's what we expect. We know that, like, aside from these sessions, there hasn't been a lot of time to be practicing it. That's okay. It's intended more, this is exposure. You're going to know a little bit of it. We'll figure out where we need to focus most on, and then we'll have a lot more practice with interview prep, like in the new year. Yeah. It'll be fine. Question? We're probably not going to cover AVL trees, yeah. But Swift Algorithm Club is a good resource for that. Yeah. Yeah. Good fun, though. Okay. Thank you all. Slag me if you got questions.